Hi everybody, today we are looking at energy fluctuations in the canonical ensemble. We have an ensemble with us, the canonical ensemble. So TV and these are the macroscopic parameters, but the energy will be actually fluctuating. The systems in the ensemble can take different values for the energy. What we are going to do is we find the energy fluctuation, how much energy is fluctuating in this ensemble. Okay, so for that a fluctuation of a quantity is given by delta F equal to F minus average value of F. So this is the average value of F. So the fluctuation of the quantity F with respect to the average value, that is delta F, that is F minus the average value of F. So if I take delta F square, that will be equal to F minus average value of F square. So that is F square plus average value of F square minus 2F average value of F. Okay, now we are again taking the average value of the square of the fluctuation. So we are taking the average value of the square of the fluctuation. So this will be average value of F square. This is F square minus 2 average value of F, average value of F. Okay, so this is equal to the average value of F square minus the average value of F square. So this is the average value of the square of the fluctuation, that is equal to average value of F square minus average value of F square. Okay, so the average value of energy, that is written as sigma r E r e to the power minus beta E r over sigma r e to the power minus beta E r. Okay, because we know e to the power minus beta E r over sigma r e to the power minus beta E r is the probability. So this is sigma r E r, this one is the average energy. So average energy square, that will be symbol is square of this. Okay, now ensemble average, or the average of E square, average of E square, energy square, that is given by sigma r E r square e to the power minus beta E r over sigma r e to the power minus beta E r. So average value E square is this. Okay, here we will have E r square, but the average value of E square is simply the square of this, because this is the average value of E. Here we will have E r. So here we are taking average value of E square, so that will be this. Okay, so keeping all these things in our mind, we find dou u by dou beta. Okay, dou u by dou beta. U is this, the average value of energy, sigma r E r e to the power minus beta E r over sigma r e to the power minus beta E r. So we find dou u by dou beta, that is, we are partially differentiating this thing with respect to beta. Beta is there in the numerator as well as in the denominator. So we have to apply the product rule. So as we apply the product rule, we will have 1 by sigma r e to the power minus beta r, and we are differentiating this thing with respect to beta. So sigma r E r minus E r will come outside, e to the power minus beta E r. The second term is sigma r E r e to the power minus beta E r, dou by dou beta of 1 by sigma r e to the power minus beta E r. So that is equal to, as we take the dou by dou beta, this will be minus of 1 by sigma r e to the power minus beta E r square, sigma r minus E r e to the power minus beta E r. So this is minus of sigma r E r square e to the power minus beta E r over sigma r e to the power minus beta E r. So we have the negative signs here, they cancel. So what we have here is sigma r e r e to the power minus beta e r over sigma r e to the power minus beta e r whole square. Okay, whole square. Okay, from this. Now this thing is, average value of E square. Okay, this is the average value of E. So average value of E square, and this thing is average value of E square. Okay, average value of E square. So what we get? Average value of E square minus average value of E square. So average value of E square minus average value E square. These two are actually different. Here we are taking average value of E and then its square. But here we are taking average value of E square. So these two are different. So this can be written as minus of this. Okay, I am taking negative sign outside. Minus of E square minus average value of E square. So this is actually delta E square. This thing, what is there in the inside the bracket, is actually expectation value of delta E square, where delta E is the fluctuation in energy. Because here we saw delta F square average value, that is equal to F square minus F minus average value of F square. Okay, where delta F is the fluctuation. So average of the square of the fluctuation is this. Here, as we look at this, it is the same way. We have the E square, average value of E square minus average value of E square. So this is delta E square average value. Okay, which is the fluctuation. Delta E is the fluctuation in energy. So delta E square, actually we started from dou U by dou beta, where volume and number of particles are constant, and we got final result as expectation value or average value delta E square. So average value delta E square is minus dou U by dou beta. Beta, we know it is 1 by kT, so this is kT square dou U by dou T to constant volume. So that is equal to kT square. This thing is the specific heat capacity at constant volume, so that is CV. Okay, so on the left hand side I have got expectation value delta E square, the fluctuation in energy square, that is equal to kT square CV. Now what I am trying to do is I take the square root of this. Okay, square root of it. So I am taking square root of it. So this is average value of the square of the fluctuation, and then we are taking the square root. Okay, so what we have is the root mean square value, because we have root and mean of the square of the fluctuation, which is the root mean square fluctuation in energy. Root mean square fluctuation energy, that is equal to root of kT square CV. Okay, root of kT square CV, and if I divide it by the average value of E, okay, if I am dividing this by average value of E, then we have the relative root mean square fluctuation. Okay, so root mean square fluctuation is relative to this. So root of kT square by CV, here U, okay, both are same, average value of energy, that is same as U. Now, if we calculate this relative root mean square fluctuation for an ideal gas, okay, for an ideal gas, CV is 3 by 2 Nk for a gas consisting of n molecules. So 3 by 2, U is 3 by 2 Nkt. So as we substitute here, the T will get cancelled. Anyway, here we have root n, and in the denominator we have n, so this is proportional to 1 by root n, or this is of the order of n to the power minus half. So relative root mean square fluctuation is of the order, this is actually representing order of n to the power minus half or 1 by root n. For large n, okay, for a large n, for large number of particles in a system. In statistical mechanics, we always consider systems having very large number of particles. So for large n, the n is very large, so this will be very, very small. So it will be very, very small, quite negligible. So relative root mean square fluctuation in energy is quite negligible. Okay, thus for all practical purposes, since the relative root mean square fluctuation is very negligible, for practical purposes, a system in the canonical ensemble has energy equal to or almost equal to the mean energy. So this canonical ensemble, the fluctuation in energy is very, very negligible. All the systems will have almost the same energy. So the situation is practically same as the micro canonical ensemble. Okay, because the fluctuation, relative fluctuation in energy is very, very small. All the systems in the ensemble will have the same energy, and in microcanonical ensemble we know all the systems have the same energy. So in the canonical ensemble, actually in the practical situations, it is identical to microcanonical ensemble. Theoretically, even though the energy can fluctuate, its relative root mean square fluctuation is very, very small. So that means all the systems in the ensemble have the same energy. So that explains why the two ensembles, the canonical ensemble and microcanonical ensemble, lead to practically identical results.